What if you could witness the very beginning of everything, not through a simulation or a theory, but by actually seeing the light that has traveled across nearly 14 billion years to reach us, the afterglow of creation itself? This is the extraordinary promise behind one of the most ambitious scientific endeavors humanity has ever undertaken, building a telescope powerful enough to see back to the Big Bang. It sounds like something out of an epic science fiction saga, but it's real. Teams of brilliant minds around the world are right now bending the laws of physics, reimagining engineering, and pushing technology into realms we once only dreamed of, all for a chance to look back in time and answer the most profound questions we can ask. Where did we come from? How did the universe begin? And what does it mean that we are here, able to ask these questions at all? This journey isn't just about building a bigger lens or a more sensitive sensor. It's about redefining the possible, to catch the whisper-faint echoes of the Big Bang, what scientists call the cosmic microwave background. We need instruments of almost unimaginable sensitivity, operating in the most extreme environments on Earth and in space. We're talking about telescopes cooled to within a fraction of a degree above absolute zero, shielded from every kind of interference, and capable of processing oceans of data in the search for patterns thinner than a ghost's breath. The challenges are monumental, touching every field of science and engineering, from quantum mechanics and material science to cryogenics and artificial intelligence. Each obstacle demands innovation, collaboration, and a kind of stubborn optimism that defines the human spirit at its best. In this video, we're going to unpack exactly what it takes to make a vision this grand into a reality. We'll explore the cutting-edge technologies being developed, the global partnerships forming to support this quest, and the sheer human determination driving it all forward. You'll get a front-row seat to the breakthroughs and setbacks, the moments of insight and ingenuity that are bringing us closer than ever to glimpsing the origin of the cosmos. This is more than a story about astronomy. It's about what happens when we dare to dream big, work together, and reach for something that connects us all to the deepest mysteries of existence. So come with us on this journey. Let's explore how humanity is building a machine that doesn't just look out into space, but back in time. Imagine a photograph taken just moments after you were born, a picture so detailed it captures not just your features but the very conditions of the room, the light, the air. Now scale that up to a cosmic level. What we are trying to capture with these telescopes is the universe's own baby picture, a snapshot of what it looked like when it was a mere 380,000 years old. Before that moment, the universe was too hot and dense for light to travel. It was an opaque, glowing fog of plasma. But as it expanded and cooled, the first atoms formed, and light was finally set free to travel across space. That first flash of light, now stretched and cooled by the expansion of the universe over billions of years, reaches us not as visible light but as a faint microwave signal that fills every corner of the sky. This is the cosmic microwave background radiation. It is the oldest light in existence, and it is all around us, a literal echo of the Big Bang that you could theoretically see as static on an old television set. Discovering this echo was one of the greatest accidents in scientific history. Back in 1965, two radio astronomers named Arno Penzias and Robert Wilson at Bell Labs in New Jersey were troubleshooting a persistent, annoying hiss in their giant horn-shaped antenna. They pointed it in every direction, and the noise was always there, day and night. They even famously cleaned out a pair of pigeons nesting in the antenna, but the noise remained. They had inadvertently stumbled upon the afterglow of creation itself, a discovery that would win them the Nobel Prize and forever change our understanding of the cosmos. This universal background hum confirmed the Big Bang theory and gave us our first tangible evidence of the universe's explosive origin. But this ancient light is far more than just a uniform glow. Embedded within it are incredibly tiny variations in temperature, tiny ripples that are only 1 part in 100,000. To put that into perspective, that's like detecting a difference in height of just a few millimeters between two mountains that are each 10 kilometers tall. These minute fluctuations are not random noise. They are the imprint of the seeds of all structure in the universe. They are the gravitational fingerprints of the slight over densities and under densities in the primordial soup that would, over billions of years, collapse under their own gravity to form everything we see today: galaxies, galaxy clusters, and the vast cosmic web that connects them. By meticulously mapping these patterns, cosmologists can read the history of the universe like a forensic scientist reads a crime scene. This is why the cosmic microwave background is the ultimate roadmap. Its patterns allow scientists to measure the fundamental ingredients of the cosmos with astonishing precision. We can determine that the universe is about 68% dark energy, 27% dark matter, and only 5% the ordinary matter that makes up stars, planets, and us. It provides a rigorous test for our theories of cosmic inflation, the idea that the universe underwent a period of exponentially rapid expansion in the first fraction of a second. Some theories of inflation predict that this violent expansion should have created ripples in spacetime itself, known as primordial gravitational waves, which would have left a distinct twisting pattern or polarization in the light of the cosmic microwave background. Finding that specific pattern is one of the holy grails of modern cosmology, a direct line back to the universe's first moment. So every single engineering challenge we will discuss, from building ultra-sensitive detectors to finding the quietest place on Earth, is in service of reading this ancient document more clearly. We are not just building a telescope, we are building a time machine to witness the birth of everything. Now, if the cosmic microwave background is our ultimate cosmic baby picture, the challenge is that this photograph is incredibly old, incredibly faint, and almost completely uniform. It's like trying to spot the microscopic brushstrokes on a masterpiece that's been painted over with a thin, nearly perfect layer of white paint. The variations we're searching for, the tiny temperature differences that hold the secrets to the universe's structure, are on the order of 1 part in 100,000. To push the analogy even further, imagine trying to measure the heat coming off a single candle sitting on the surface of the moon from your backyard here on Earth. That's the astronomical level of sensitivity we're talking about achieving. Our current generation of telescopes, like the incredible Planck satellite launched by the European Space Agency, have done a heroic job. Planck gave us our most detailed all-sky map of this ancient light, a map so precise it looks like a marbled work of art. But even with this phenomenal achievement, we've reached the limits of what these instruments can tell us. They've answered the questions of the 20th century, but they've also highlighted the new, more profound questions of the 21st. To probe the mysteries of cosmic inflation and to hunt for the telltale signs of primordial gravitational waves, we need to see this map with a clarity that is an order of magnitude or even 100 times better. We need to push past the blur and see the universe's first moments in ultra-high definition. So how do we break through this barrier? The answer lies in a two-pronged attack on the problem: resolution and sensitivity. First, we need to collect more light, a lot more light. This means building telescopes with much larger collecting areas, whether that's through enormous, exquisitely polished mirrors or vast arrays of smaller antennas working in concert. A bigger bucket catches more rain, and a bigger telescope catches more of these precious, ancient photons. Projects like the upcoming CMB S4 experiment envision deploying an army of telescopes in the high deserts of Chile and the South Pole, creating a collective eye on the sky with unprecedented light-gathering power. But making the telescope bigger is only half the battle. The other, even more critical half, is making the detectors themselves almost unimaginably sensitive and quiet. Every object with any heat at all gives off thermal radiation, which creates a constant hissing static of noise that can easily drown out the faint cosmic signal we're after. To silence this hiss, we have to make the detectors incredibly cold. We're not talking about your kitchen freezer cold. We're talking about a fraction of a degree above absolute zero, the theoretical point where all atomic motion stops. At temperatures below 0.1 Kelvin, the thermal noise of the detectors themselves is reduced to a barely perceptible whisper, allowing the even fainter whisper of the Big Bang to finally be heard. Achieving and maintaining this deep cold is a monumental engineering feat in itself, requiring sophisticated cryogenic systems that often use rare isotopes of helium in complex, multi-stage refrigerators. And the detectors themselves are marvels of modern physics. They are often built from superconducting materials which, when chilled to these extreme temperatures, lose all electrical resistance. This allows them to act as exquisitely sensitive thermometers, capable of registering the minuscule amount of heat deposited by a single photon of microwave light. Designing a system that can not only measure a temperature change of 1/1000th of a degree, but also do it reliably from a remote mountaintop or in the vacuum of space, is what consumes the lives of hundreds of engineers and scientists. It's a painstaking process of innovation, where a breakthrough in materials science or a new design for a quantum amplifier can shave off just enough noise to finally see what was previously invisible. This relentless pursuit of perfection, component by component, is what will ultimately build a window to the beginning of everything. So you've built this incredibly sensitive instrument, a machine chilled to near absolute zero and capable of detecting a signal 1,000,000,000 times fainter than any previous telescope. You're ready to listen to the universe's first whisper, but the moment you turn it on, all you hear is a deafening roar. This is the second monumental challenge. The universe and our own planet are incredibly loud places. Our delicate cosmic signal is buried under a cacophony of noise from Earth's atmosphere, human technology, and even high-energy particles screaming across the galaxy. It's like trying to hear a pin drop in the middle of a heavy metal concert. To have any hope of success, we must find or create a place of profound silence. The first and most obvious source of interference is right above us, Earth's atmosphere. While it protects us, it's a shimmering, shifting veil of gases that absorbs and distorts the very microwaves we're trying to measure. Water vapor is a particular villain as it emits its own microwave radiation, effectively blinding our instruments. The solution is to get above as much of this atmosphere as possible. This is why you'll find the world's premier cosmic microwave background observatories perched in the most extreme, high-altitude deserts on Earth. Places like the Atacama Desert in Chile, home to the Simons Observatory, sit at an altitude of over 5,000 meters. At that height, the air is so thin and dry that it's one of the most transparent windows to the cosmos on the planet. It's not a perfect solution, but it gets us significantly closer to the silence we need. But for the ultimate quiet, we have to leave Earth entirely. Space offers a near-perfect vacuum, free from atmospheric interference. This was the logic behind missions like Planck, which orbited at a stable point in space called L2, about 1.5 million kilometers away. From that distant vantage point, shielded by its own spacecraft body from the noise of the sun, Earth, and Moon, Planck could listen to the cosmos with a clarity impossible from any mountaintop. Future missions like the proposed Lightbird aim to go even further, designed specifically to operate in the pristine quiet of space to hunt for the elusive polarization patterns from inflation. However, escaping Earth's atmosphere doesn't mean escaping all noise. Human civilization is constantly broadcasting a torrent of radio frequency interference, everything from television and radio signals to cell phone towers and satellite communications. These signals are billions of times stronger than the cosmic microwave background and can easily swamp the detectors. This is why remote locations are chosen not just for their altitude, but for their isolation. The South Pole Telescope, for instance, benefits from the natural radio silence of Antarctica, but even there, the telescope itself must be meticulously shielded. Its components are often enclosed in specially designed enclosures that act like a Faraday cage, blocking out any stray man-made radio waves and creating an artificial bubble of radio silence around the instrument itself. And then there's the noise that comes from beyond our planet, cosmic rays. These are high-energy particles, often protons, that streak across the universe at nearly the speed of light. When one slams into a detector, it deposits a significant amount of energy, creating a sharp, spiky signal that can mimic or completely obliterate the gentle cosmic whisper we're seeking. Shielding against this requires a different approach. While lead shielding might work in a lab on Earth, it's too heavy for space missions. Instead, engineers use clever filtering techniques in their data analysis, developing sophisticated algorithms that can recognize the unique fingerprint of a cosmic ray hit and digitally remove it from the data stream. It's a constant game of cat and mouse, identifying new sources of noise and inventing new ways to subtract them. This relentless pursuit of silence is what transforms a powerful telescope from a deafened giant into a keen-eared listener. It's not merely about finding a remote location. It's a holistic effort involving geographic strategy, advanced materials for shielding, and complex software for filtering. Every layer of protection, every algorithm refined, is about carving out a smaller and smaller bubble of tranquility in a chaotic cosmos. We are, in effect, building a sanctuary for a sound, a carefully guarded quiet where the oldest story in the universe can finally be heard without interruption. But building a quiet observatory is only part of the solution. To actually hear the universe's faintest whisper, you need an incredibly sensitive ear. This brings us to the true heart of the telescope, its detectors. These aren't simple light sensors. They are arguably the most advanced scientific instruments ever conceived, engineered to measure the unmeasurable. Their sole purpose is to detect temperature changes in the cosmic microwave background so minuscule they defy everyday comprehension. We're talking about differences of a few microkelvins, or 1/1,000,000th of a degree. To put that into a human scale, it's the energy equivalent of detecting the heat from a single birthday candle from a distance of over 600 miles. Achieving this level of sensitivity requires us to move beyond conventional electronics and into the strange and counterintuitive world of quantum physics and superconductivity. The workhorses of this new era are detectors like transition edge sensors, or TESS, and kinetic inductance detectors, often called KIDs. Both rely on a remarkable phenomenon, superconductivity. When certain materials are cooled to those cryogenic temperatures near absolute zero, they undergo a dramatic transformation. Their electrical resistance doesn't just get low, it completely vanishes. Electricity can flow through them forever without any loss. This superconducting state is incredibly delicate, poised on a knife's edge. For a transition edge sensor, engineers carefully tune a tiny strip of superconducting material like tungsten to sit right at the precise temperature between its normal and superconducting states. When a single photon from the cosmic microwave background strikes this strip, it deposits a minuscule amount of heat. This tiny jolt of energy is enough to bump the material out of its superconducting state, causing a measurable change in its electrical resistance. It's an exquisitely sensitive quantum thermometer, translating the faintest whisper of heat into a clear electrical signal we can record. Kinetic inductance detectors work on a different but equally fascinating principle. In a superconductor, electrical current doesn't just flow through the material. It's carried by pairs of electrons known as Cooper pairs. A KID is essentially a tiny superconducting resonator, a circuit that naturally vibrates at a specific radio frequency. When a photon hits it, it breaks apart some of these Cooper pairs. This changes the resonator's properties, slightly shifting its natural vibration frequency. By meticulously tracking these tiny frequency shifts, scientists can count individual photons and measure their energy. The advantage of KIDs is that thousands of these resonators can be read out using a single transmission line, making them ideal for the massive arrays needed for next-generation telescopes. Building these detectors is a feat of nanotechnology. They are not machined, they are grown and etched using the same sophisticated processes that create computer microchips. Researchers are experimenting with novel materials like nitrides and silicides, fabricating structures so small they operate at the quantum limit, where the Heisenberg uncertainty principle starts to dictate what is possible. To amplify the incredibly weak signals from these detectors without adding noise, engineers are developing quantum-limited amplifiers. These devices use the principles of quantum mechanics to amplify a signal so that it adds the absolute minimum amount of extra disturbance allowed by the laws of physics itself. This isn't just incremental improvement. It's a fundamental rethinking of measurement, pushing up against the boundaries set by nature. The scale of this effort is breathtaking. The Bicep Array telescope at the South Pole, for instance, doesn't have a few dozen or a few hundred of these detectors. Its latest camera contains over 32,000 individual polarized detectors, all working in unison. Each one of those 32,000 pixels is a masterpiece of precision engineering. Each must be perfectly calibrated and characterized because a single malfunctioning detector can introduce a false signal that could be mistaken for a monumental discovery. This creates an immense logistical challenge. Every detector must be tested at cryogenic temperatures before installation, its response meticulously mapped and recorded. The data from each pixel must be read out and processed without crosstalk or interference from its neighbors. It's a symphony of ultra-sensitive components, each playing its part in perfect harmony to create a single, coherent picture of the primordial universe. This relentless pursuit of sensitivity is what transforms a theoretical dream into tangible, reliable data, bringing us one step closer to touching the dawn of time. Now consider the sheer volume of information this symphony of detectors produces. Each of those 32,000 pixels isn't just taking a single picture. It's scanning the sky continuously, measuring the intensity and polarization of microwave light millions of times per second. This relentless data collection doesn't just add up, it multiplies into an ocean of ones and zeros. We are talking about a true data deluge, a flood of information so vast it's measured in petabytes. To put that in perspective, a single petabyte is enough to store over 200,000 DVD-quality movies. A next-generation cosmic microwave background experiment can generate that much data in a single year of operation. This isn't a side effect of the science, it is the very heart of it. The raw output from the telescope is just noise. The real magic, the act of transforming that electronic hiss into a clear image of the infant universe, happens inside some of the world's most powerful supercomputers. The journey from raw data to cosmic revelation is a long and arduous one, a multi-stage purification process. The first challenge is that the signal from the cosmos is hopelessly entangled with noise from the instrument itself. Every detector has its own unique personality, its own slight biases and drifts over time. The amplifiers add their own characteristic electronic hum. Even the subtle warming and cooling of the telescope structure as it moves across the sky can introduce false signals. Before cosmologists can even think about testing theories of the Big Bang, teams of data scientists must perform a painstaking digital cleanup, subtracting all these known instrumental effects. It's like trying to isolate the sound of a single violin in a massive orchestra, recording by carefully removing the sound of every other instrument one by one, based only on a vague understanding of what each one should sound like. This initial processing is so computationally intensive and so time-sensitive that it often can't wait. At remote observatories like the South Pole Telescope, they've had to build their own supercomputing clusters right there on the ice. Imagine a server room humming away in one of the most isolated and hostile environments on Earth, where the outside air is so cold that keeping the computers from overheating becomes a unique challenge. These on-site computing behemoths perform the first crucial steps, converting the raw detector signals into a manageable form, applying initial filters, and performing basic quality checks to ensure the telescope is operating correctly. Only then is the partially refined data transmitted via satellite link to research institutions around the world for the deep analysis, and this is where the real heavy lifting begins. Cosmologists use immensely complex algorithms to convert millions of time-ordered data points into a map of the sky. This process, known as mapmaking, is a monumental inverse problem. The telescope doesn't just take a simple picture, it scans back and forth with each detector measuring a point in the sky at a specific time. The software's job is to take this gigantic, tangled list of measurements and reassemble it into a coherent, two-dimensional image, all while keeping track of and removing any residual noise. It's an operation that can require thousands of central processing units running for months on end. This is also where artificial intelligence and machine learning are revolutionizing the field. Traditional algorithms are powerful, but they struggle with certain types of complex, non-linear noise. Neural networks trained on vast simulations of both the cosmic signal and every conceivable type of instrumental noise are now being deployed. They can learn to recognize and filter out subtle interference patterns that would be almost impossible for a human to code for explicitly. They act like supremely talented audio engineers, listening to the cosmic static and using their trained intuition to isolate the true music of the spheres from the cacophony of distortion. This processed map is the final, precious product, but the journey isn't over. This map then becomes the input for another set of algorithms designed to compare it against billions of different theoretical models of the universe, searching for the one whose predicted patterns of primordial ripples most closely match what we actually see in the sky. Every single step from the first bit of data to the final cosmological parameter is a testament to our ability to not just collect information, but to find meaning within it. But all that phenomenal data processing power would be meaningless if the detectors themselves were drowning in their own internal noise. This is where we encounter one of the most physically demanding challenges of the entire endeavor, the absolute, non-negotiable requirement for extreme cold. We're not talking about a winter's day or even the deep freeze of Antarctica. To silence the random jiggling of atoms within the detectors themselves, a phenomenon known as thermal noise. We have to bring them to within a hair's breadth of the coldest temperature possible in the universe, absolute zero. This isn't a suggestion, it's a fundamental law of physics. Heat is motion, and motion is noise. To hear the faintest whisper from the cosmos, we must achieve near-perfect stillness. The numbers involved are almost abstract in their extremity. While your home freezer operates at around 255 Kelvin, and the void of space is a chilly 3 Kelvin, the detectors for a cosmic microwave background telescope must be cooled below 0.1 Kelvin. To grasp how cold that truly is, consider that the coldest naturally occurring place in the known universe is the depths of outer space, at roughly 2.7 Kelvin. We are aiming for temperatures over 25 times colder than the vacuum between galaxies. At these extremes, the very concept of cold changes. It's not about removing chill, but about arresting almost all atomic motion, creating an environment of profound quantum stillness where the faintest signal can finally be distinguished. Achieving this on a laboratory bench is difficult enough. Doing it for a massive array of thousands of detectors, housed in a telescope that might be sitting on a remote mountaintop or hurling through the vacuum of space, is a monumental feat of thermal engineering. The workhorses for this task are not simple compressors but incredibly sophisticated machines like dilution refrigerators and adiabatic demagnetization refrigerators. A dilution refrigerator is a masterpiece of precision, using a mixture of the two isotopes of helium, helium-3, and helium-4. By carefully manipulating the pressure and temperature of this mixture, engineers can exploit its quantum properties to continuously pump heat away from the instrument stages, reaching temperatures as low as 0.01 Kelvin. It's a closed-loop system that can run for years, but it's also mechanically complex and requires a steady supply of rare and expensive helium isotopes. For space missions where reliability and minimal moving parts are paramount, adiabatic demagnetization refrigerators, or ADA, often become the technology of choice. An ADR operates on a beautifully elegant principle. It uses a powerful magnet to align the magnetic moments of atoms in a special salt pill, effectively putting them into a very low entropy, ordered state. When the magnetic field is slowly or adiabatically removed, the atoms must absorb thermal energy from their surroundings to return to a disordered state. This process literally pulls heat out of the attached detectors, cooling them down. The cycle can then be repeated. ADRs have very few moving parts, making them exceptionally reliable for missions where a repair is impossible. The challenge intensifies when we consider scale. Cooling a single small detector is one thing. Cooling a focal plane that holds tens of thousands of them, along with the associated readout electronics, is an entirely different problem. The cooling system must have enough power to overcome the inevitable heat leaks and the tiny but cumulative heat generated by the electronics themselves. Every wire, every strap, every structural support is a potential highway for heat to flow back into the system. Engineers spend countless hours modeling these thermal pathways, using materials with exceptionally low thermal conductivity, and designing intricate radiation shields to block the subtle but persistent heat radiated by the warmer outer stages of the instrument. Consider the proposed Light-Bird space mission. Its goal is to operate for years at the Earth-Sun L2 point, over 1 million miles away. Its entire mission hinges on a multi-stage cooling system that must work flawlessly from launch to decommissioning. The plan involves a chain of coolers, perhaps mechanical pulse tube coolers to get to around 4 Kelvin, followed by a Joule-Thomson cooler to reach 1.5 Kelvin, and finally a sophisticated ADR to plunge the most sensitive detectors down to their operational temperature of 0.1 Kelvin. This entire thermal ladder must be incredibly power efficient, as it runs on the limited energy provided by the spacecraft's solar panels. A single point of failure in this chain could mean the loss of the entire multi-billion-dollar mission. This isn't just about staying cold, it's about orchestrating a symphony of thermal management, where every component from the largest tank of coolant to the smallest wire must perform in perfect harmony for years on end, all to create a tiny island of profound cold in the vastness of space, an island quiet enough to finally hear the birth of the universe. But building a super-sensitive, super-cold ear is only useful if you also give it a giant, perfectly shaped ear trumpet to collect every possible whisper. This brings us to the next monumental hurdle, the optics. We need to gather an enormous amount of this incredibly faint light, which means we need telescopes with huge collecting areas. We're not talking about the delicate lenses of a backyard telescope. We're talking about building massive, near-perfect mirrors, often several meters across, that can operate in the deep cold of space or the Antarctic winter without warping even a fraction of a human hair. It's a challenge that pushes the limits of material science and precision engineering, demanding a flawless surface shaped not just for visual perfection, but for the unforgiving demands of the microwave spectrum. Think of it like this: the cosmic microwave background is a gentle, omnipresent rain of photons falling on Earth from all directions. To study its subtle patterns, we need to catch as many of these raindrops as possible. A small bucket, a small telescope aperture, simply won't collect enough for a meaningful measurement. We need a massive rain barrel. For the next generation CMB-S4 project, that means designing telescopes with primary mirrors up to 6 meters in diameter. That's wider than most living rooms, a colossal dish that must be sculpted and polished to an almost unimaginable degree of perfection. Any microscopic imperfection on its surface, a tiny bump, a shallow dip, a subtle ripple will scatter incoming photons and distort the final image, smearing the very primordial details we're desperate to see. And the challenge is compounded by the environment. These mirrors can't just be perfect in a clean, temperature-controlled lab. They have to stay perfect while being cooled to cryogenic temperatures, where most materials contract and can warp unpredictably. Imagine taking a beautifully flat sheet of metal and throwing it into liquid nitrogen. It might bend, twist, or crack. For a telescope mirror, that kind of deformation would be catastrophic. This is where the choice of material becomes absolutely critical. Engineers can't use ordinary glass. Instead, they turn to advanced materials with exceptionally low coefficients of thermal expansion, meaning they barely change size or shape with temperature swings. Aluminum is a common choice for its good thermal properties and ease of machining, but it's heavy. For larger mirrors, the quest often leads to silicon carbide or carbon fiber composites, incredibly stiff, incredibly lightweight materials that are notoriously difficult to work with but remain stable across the enormous temperature gradients they will endure. The fabrication process itself is a breathtaking blend of brute force and atomic scale finesse. Creating a 6-meter mirror blank from a material like silicon carbide is a feat of industrial engineering. But the real magic happens in the polishing. Using a combination of computer-controlled machines and, astonishingly, still relying on the skilled hands of master opticians, the surface is ground and polished for months, even years. The goal is a surface so smooth that if you were to blow it up to the size of North America, the tallest mountain or deepest valley would be no more than a few inches high. This atomic scale smoothness ensures that microwaves are reflected and focused with absolute precision, not scattered away into nothingness. This immense, flawless mirror is just the beginning. The entire optical system, including secondary mirrors, lenses, and the structures that hold them, must be designed with the same obsessive attention to thermal stability and mechanical rigidity. Every component must be modeled and tested to ensure that as the entire telescope cools from room temperature to near absolute zero, everything contracts in perfect, harmonious unison, maintaining the precise alignment down to micron-level tolerances. It's a symphony of engineering where materials science, mechanical design, and optical physics converge to create a single, giant eye. An eye capable of gathering the faintest glimmers of light from the dawn of time and focusing them onto those waiting, ultra-cold detectors, ready to tell us their ancient story. Yet even with flawless optics and exquisitely sensitive detectors, the data faces a final, insidious threat. Not noise from the outside, but subtle, deceptive errors born from the instrument itself. Imagine a master painter trying to reproduce a scene while looking through a pair of glasses with a tiny, almost invisible scratch on one lens. No matter how skilled the artist, that scratch will introduce a faint, repeating flaw into every single brushstroke. For our cosmic telescope, these scratches are called systematic errors. They are not random. They are consistent biases introduced by the slightest imperfection in the telescope's design, its environment, or its operation. A mirror might have a minuscule, undetected warp. The cryogenic system might cause a detector to drift minutely in its sensitivity over the course of a day. Even the way the telescope scans across the sky can leave a preferred directional pattern in the data. These errors are particularly dangerous because they can masquerade as a real cosmic signal. A faint, repeating pattern from a vibrating component could be mistaken for the long-sought polarization signature of primordial gravitational waves, leading to a false discovery of monumental proportions. The entire multi-billion-dollar, decades-long endeavor could be invalidated by a single, unaccounted-for quirk of the machinery. This is why the battle against systematics is a war fought on two fronts, through relentless physical calibration and through the power of digital simulation. Calibration is the process of giving the telescope a known signal to measure, a kind of cosmic ruler against which it can check its own accuracy. The most reliable rulers are often celestial objects themselves. Astronomers will periodically point their ultra-sensitive microwave telescopes at something like the planet Jupiter. Why Jupiter? Because its brightness and temperature in the microwave spectrum are extremely well known and stable. It acts as a brilliant, reliable beacon in the sky. By observing it and comparing what the telescope sees to what we know Jupiter should look like, engineers can identify and quantify any distortions their instrument is adding. They can ask, is our focus perfect? Are our detectors responding linearly? Is the beam shape what we designed it to be? The answers allow them to build a precise error model, a mathematical filter that can be applied to all the subsequent data to remove the instrument's own personality from the results. Some projects take this even further. The Atacama Cosmology Telescope doesn't just occasionally look at Jupiter. It has an entire dedicated, smaller telescope sitting right beside its main dish, a constant companion whose sole job is calibration. This smaller scope continuously monitors known, stable sources, providing a real-time health check on the atmosphere's transparency and the overall system's performance. It's like having a master watchmaker constantly looking over your shoulder, adjusting your tools as you work to ensure every measurement is perfect. But calibration isn't just about looking outward. Engineers also build artificial calibration sources directly into the telescope itself. These can be tiny, heated filaments or even small microwave emitters that produce a known signal. By periodically activating these sources and recording how the detectors respond, the team can track minute changes in sensitivity, a drift of a fraction of a percent over hours, days, and years, and correct for it. Alongside this physical checking, an immense effort takes place inside supercomputers. Before a single piece of metal is even cut for a new telescope, engineers build a staggeringly detailed digital twin of the entire instrument. This virtual telescope exists entirely in code. They simulate everything: the exact shape of the microwave beams, the thermal contraction of every bolt and wire as it cools, the subtle vibrations from motors, the impact of cosmic rays striking the detectors, even the way light might scatter off the inside of the telescope tube. They then feed this digital twin a perfect, simulated map of the cosmic microwave background and tell it to observe it. The computer then outputs what the real telescope would see, complete with all the simulated systematic errors baked in. The scientists then practice their entire data analysis pipeline on this flawed, artificial data set. Their goal is to see if their analysis methods can successfully strip away all the added errors and recover the original, pristine sky map they started with. If they can't, they know they must go back to the drawing board, either redesigning the hardware to eliminate that particular systematic or improving their software to better recognize and remove it. This process of virtual testing is what transforms a good telescope into a great one, ensuring that when it finally opens its eye to the sky, the truth it reveals is the universe's and not its own. But even after you've designed the perfect instrument, conquered the noise, and engineered a system of flawless precision, you are faced with a challenge that no amount of physics or computing power can solve alone: the challenge of bringing the world together to pay for it. The sheer scale of these endeavors places them far beyond the reach of any single university, any single company, or even any single nation's space agency. We are talking about projects with price tags that run into the billions of dollars and timelines that span decades, from initial concept to final deployment. This isn't just expensive science, it's a generational investment on par with building a particle accelerator or sending humans to the moon. And securing that level of commitment requires a different kind of engineering altogether: the engineering of persuasion, diplomacy, and shared vision. The journey for funding begins not in a lab, but in committee rooms and legislative halls. Scientists and project leaders must become evangelists, translating the profound but abstract goals of fundamental cosmology into a narrative that resonates with politicians, government agencies, and private philanthropists. They have to answer the inevitable and often frustrating question: what is the tangible return on investment? The answer isn't found in a new consumer gadget or an immediate medical cure. Instead, it lies in the currency of inspiration, knowledge, and technological spin-offs. They argue that the quest to understand our origins is a fundamental human drive, one that inspires generations of students to pursue careers in science, technology, engineering, and mathematics. They point to the countless technological innovations that were pioneered for space and astronomy, from improvements in medical imaging to the development of the charge-coupled device that powers every digital camera that later revolutionized everyday life. It's a long game, a bet on the intangible value of expanding the boundaries of human knowledge. This process is a roller coaster of hope and setback. A project might spend years in what's called the pre-phase A stage, a conceptual limbo where teams write endless white papers and proposals, meticulously detailing the science goals and technical feasibility. They present these to review panels at organizations like the National Science Foundation or NASA, where they are pitted against other worthy projects in a fierce competition for limited resources. A single negative review or a shift in political priorities can delay a project for years or kill it entirely. The successful ones, like the recently launched James Webb Space Telescope, demonstrate the payoff of persistence. Its development was plagued by massive cost overruns and repeated delays, pushing its total cost near $10 billion and testing the patience of lawmakers. But its stunning success has now vindicated that investment, making the case for the next great observatory that much stronger. Given these astronomical costs and risks, international collaboration isn't just beneficial, it's essential. No single country should or could bear the entire financial and technical burden alone. This is why the most ambitious projects are inherently global. The James Webb Space Telescope stands as a monumental testament to this principle. While led by NASA, it was fundamentally a partnership with the European Space Agency, which provided the powerful Ariane 5 rocket for launch, and the Canadian Space Agency, which contributed a critical fine guidance sensor. This model distributes the financial risk and pools the world's best expertise, but it also introduces a layer of immense logistical and diplomatic complexity. Suddenly, your project timeline is tied to the budgetary cycles of multiple nations. Technical teams are spread across a dozen time zones, requiring meetings at all hours and a constant, careful dance of communication to ensure everyone is aligned. Navigating these cultural and bureaucratic differences is a soft skill as critical as any hard engineering discipline. Different countries have different engineering standards, different management styles, and different priorities. A component built in one nation must integrate perfectly with a system built in another, often after traveling thousands of miles. This requires an unprecedented level of trust and coordination. Contracts must be negotiated, intellectual property agreements must be settled, and the all-important question of data rights must be decided upfront. Who gets access to the data first, and how will it be shared with the global community? It's a delicate balancing act, ensuring that all partners feel they are getting a fair return on their investment, while keeping the primary scientific mission front and center. Ultimately, this human dimension, the ability to build consensus, secure funding, and foster collaboration across borders, is what transforms a brilliant idea on a whiteboard into steel, silicon, and data. It is the foundation upon which everything else is built. The telescopes that see back to the Big Bang are not just monuments to our technical ingenuity. They are monuments to our ability to work together on a global scale, to pool our resources and our intellects in pursuit of answers to the biggest questions we can ask. They prove that when humanity chooses to focus on a common, inspirational goal, we are capable of achieving the seemingly impossible. After years of meticulous design and construction, the telescope is finally complete, a perfect, pristine instrument of unimaginable sensitivity. But its journey has only just begun. For a space-based observatory, the single most dangerous part of its entire existence is the few minutes it spends strapped to a controlled explosion, hurtling out of Earth's atmosphere. The launch is a violent, unforgiving gauntlet of noise, vibration, and extreme forces that threatens to shake the most precisely aligned components to pieces. Imagine securing a priceless, hand-blown glass sculpture to the top of a jackhammer and turning it on to its highest setting. That is the reality of a rocket launch. Every bolt, every wire, every microscopic superconducting detector must be engineered not just for the profound cold and quiet of space, but to survive the deafening roar and brutal shaking of the ride there. The primary villain during ascent is vibration. The immense power of the rocket engines, combined with the turbulence of punching through the atmosphere at thousands of miles per hour, creates a chaotic symphony of shaking that resonates through the entire structure. Engineers spend countless hours identifying the natural vibrational frequencies of every single component of the telescope, from the largest mirror to the smallest electrical connection. They then use sophisticated computer models to simulate the launch environment, predicting how these vibrations will interact and amplify each other. The goal is to avoid any phenomenon called resonance, where the shaking from the rocket matches the natural frequency of a part, causing its vibrations to intensify catastrophically, like an opera singer shattering a wine glass. To prevent this, they often literally shake the entire assembled telescope on a massive vibration table, a test that can feel like a form of technological torture, but is absolutely essential to uncover any hidden weakness before it's too late. Alongside the shaking comes the crushing force of acceleration, or G-forces. As the rocket pushes against Earth's gravity, everything on board is pressed down with a force several times that of normal gravity. This isn't just a feeling, it's a physical load that can bend structures, compress materials, and put immense strain on delicate supports. The telescope's massive primary mirror, for instance, must be mounted in a way that it can withstand these forces without flexing even a micron out of shape. Often, special launch locks are used, heavy-duty clamps and supports that hold everything in a rigid, safe configuration during the violent ascent. These locks are then designed to pyrotechnically release or motorize away once in the gentle embrace of microgravity, a crucial step that itself carries risk. If a single launch lock fails to disengage, the entire mission can be left with a telescope that is permanently stuck in its launch configuration, a multi-billion-dollar instrument rendered useless. Then comes the most heart-stopping phase of all, deployment. Unlike the iconic Hubble Space Telescope, which was largely a single, solid cylinder, modern observatories designed to see the Big Bang are often too large to fit inside any rocket's payload fairing. They must be designed to fold up origami-like for launch and then perform a complex, automated ballet of self-assembly in the void of space. The James Webb Space Telescope's deployment sequence was a masterpiece of this engineering art, involving over 300 single-point failure items mechanisms that had to work perfectly with no backup. It unfolded in a series of high-anxiety steps: the extension of its solar panel, the precise unfurling of its multi-layered sunshield the size of a tennis court, the delicate hinging of its enormous golden mirror segments into their final, perfect alignment. Each of these actions was commanded from over 1 million miles away, with a communication delay that made real-time intervention impossible. The entire process had to be pre-programmed and autonomous, a dance of motors, pulleys, and cables that had been rehearsed thousands of times on Earth under simulated zero-gravity conditions. The margin for error in this celestial ballet is effectively zero. A single stuck hinge, a snagged cable, or a misbehaving sensor could spell instant doom for the mission. This is why redundancy is baked into every critical system wherever possible, and why testing is so exhaustive. Engineers don't just test the components, they test the full deployment sequence over and over again, in giant thermal vacuum chambers that simulate the extreme temperatures and airless conditions of space. They test until the process becomes boringly reliable, because in space, boring is beautiful. Excitement is what you desperately want to avoid. They also simulate worst-case scenarios, planning contingency commands that can be sent up to coax a reluctant mechanism into action, or to gently shake the spacecraft to free a stuck component. This phase is a high-wire act without a net, where decades of work and the hopes of a global scientific community hinge on the flawless performance of a few dozen motors and latches. It is the ultimate test of human ingenuity, a moment where engineering must triumph over an environment of pure chaos to create a new eye on the cosmos. And surviving the violent ascent is only the beginning of the mission. Once a telescope reaches its orbital perch or begins its long vigil from a remote polar plateau, it enters a new phase defined by one simple, brutal fact: it is almost entirely on its own. Unlike a car or even a satellite in near-Earth orbit, you can't simply send a repair crew to fix a problem. For a space telescope orbiting 1 million miles away at Lagrange point 2, a service mission is physically impossible with today's technology. For a ground-based instrument like the South Pole Telescope, the environment itself becomes a prison for 8 months of the year, with temperatures plummeting to -80 degrees Fahrenheit and complete darkness, making any travel to or from the base an unthinkable risk. This reality forces engineers to adopt a completely different design philosophy from the very start. Every single component must be built not just for optimal performance, but for ultimate survival. This begins with a concept called designing for reliability. Every piece of the telescope, from the largest mirror actuator to the smallest data cable connector, is subjected to a rigorous process of failure mode analysis. Engineers ask a simple but haunting question for every part: how could this fail, and what would the consequence be? For critical systems, the answer cannot be "the mission ends." Instead, the solution is redundancy. If one gyroscope fails, another identical one is ready to spin up and take its place. If a primary computer crashes, a backup unit, often hardened against radiation, is standing by to seamlessly assume control. This isn't just duplication, it's often triplication or even quadruplication for the most vital functions. Power systems, communication transponders, and data storage drives are all cross-linked so that a single point of failure cannot silence the entire observatory. This layered approach to reliability turns the telescope into a resilient entity, capable of weathering internal failures without missing a beat in its cosmic listening. The harsh environment of space adds another layer of relentless assault. Beyond the vacuum and extreme cold, there is the constant, invisible barrage of high-energy radiation from the sun and distant cosmic sources. This radiation can literally fry delicate electronic circuits, causing bit flips in memory, degrading solar panels, and slowly damaging detector materials. To combat this, engineers don't use commercial off-the-shelf computer chips. They use radiation-hardened electronics, components specifically designed and manufactured to withstand these particle storms. These rad-hard chips are slower, more expensive, and generations behind consumer technology, but their resilience is what guarantees the telescope's long-term brain function. Similarly, the telescope's software is built with immense robustness. It includes countless watchdog timers and fault protection routines that constantly monitor the health of the system. If it detects an anomaly, a temperature reading that's slightly off, a pressure sensor that seems stuck, it doesn't wait for a command from Earth. It is programmed to autonomously take action, perhaps switching to a backup system, putting the telescope into a safe mode, and then radioing home for help. This autonomy is the telescope's immune system, allowing it to diagnose and contain problems before they become fatal. For the heroic winter over crews at places like the Amundsen Scott South Pole Station, maintenance is a brutal, hands-on affair. When something breaks during the long polar night, they are the only ones who can fix it. These small teams of engineers and technicians are selected not just for their technical skill, but for their mental fortitude to endure months of isolation and extreme cold. Repairing a motor on a telescope mirror might involve suiting up in multiple layers of extreme cold weather gear, working with specialized tools that can still function at temperatures that instantly freeze bare skin, and completing the job quickly before frostbite sets in. Their work is a testament to human ingenuity and courage, a direct physical intervention to keep the data flowing from one of the most hostile workplaces on the planet. In the void of space, the only tools for maintenance are digital. Software updates become the primary method for fixing problems and even upgrading performance. Teams on Earth can beam up new code patches to work around a malfunctioning component, to improve the efficiency of a scanning pattern, or to enhance the onboard data processing algorithms. Remote diagnostics are a constant activity. Engineers spend their days poring over thousands of channels of telemetry, data, voltages, temperatures, pressures, and current readings, searching for the slightest sign of wear or drift that might indicate a component is beginning to fatigue. This slow, meticulous analysis of the telescope's vital signs is like a doctor performing a perpetual annual physical from a distance of 1,000,000 miles, using the data to predict and prevent illnesses before they ever show a symptom. This unwavering focus on endurance transforms the telescope from a fragile instrument into a persistent observer, a sentinel that can watch the ancient sky for years on end, its value growing with every additional day of data it provides. Now consider the sheer diversity of minds required to bring such a machine to life. An astrophysicist might dream of measuring primordial gravitational waves, but it falls to a mechanical engineer to design a mount that can point a 6-meter mirror with micron precision in -80-degree weather. A data scientist develops algorithms to filter cosmic rays, while a materials expert searches for a substance that won't warp when cooled to near absolute zero. This isn't just a team, it's a miniature United Nations of expertise where each member speaks a different technical dialect and views the problem through an entirely different lens. The cosmologist thinks in terms of statistical significance and sigma levels, the cryogenic engineer in terms of thermal loads and helium flow rates, and the software developer in terms of code efficiency and database architecture. The monumental challenge isn't just assembling this dream team, it's getting them to understand each other well enough to build a single, coherent instrument instead of a collection of incompatible parts. The friction points are often found in the translation of needs into specifications. An astronomer might request a detector with the highest possible sensitivity, a phrase that sounds perfectly clear. To the engineer, this translates into a cascade of concrete requirements. It means the detector must operate at 0.1 Kelvin, which necessitates a 4-stage cryocooler, which demands a certain amount of electrical power and creates specific vibrational frequencies that could interfere with the very measurements they're trying to make. A seemingly simple request can send ripples through every other subsystem. This is where the abstract goal of seeing the Big Bang gets grounded in the gritty reality of trade-offs. Perhaps achieving that last fraction of sensitivity would require a cooling system so large and power-hungry it would make the entire spacecraft too heavy to launch. The team must then collectively decide, where do we make the compromise? These are not easy conversations. They require a shared language and a deep, mutual respect for the constraints of each other's domains. It's a constant process of negotiation and education, where the physicist must learn enough about structural engineering to understand why her ideal mirror shape is impossible to support, and the engineer must learn enough cosmology to understand why a particular optical design is non-negotiable for the science. Bridging these communication gaps requires more than goodwill. It requires structure and tools. Large collaborations often employ systems engineers as professional translators, individuals whose entire job is to move between disciplines, ensuring the scientist's vision is accurately interpreted by the engineers and that the engineers' practical limitations are clearly understood by the scientists. They create vast, living documents that track thousands of requirements, tracing a line from the lofty scientific goal all the way down to the specific tensile strength of a single bolt. Regular, mandatory design reviews bring everyone into the same room, either physically or virtually, forcing conversations that might not happen otherwise. Digital collaboration platforms become the central nervous system of the project, a shared space where an electrical engineer in California can post a circuit diagram for a detector readout and a physicist in Japan can immediately comment on how its noise profile might affect her ability to measure a polarization signal. This digital glue is what holds the sprawling enterprise together, turning a cacophony of individual expertise into a harmonious symphony of coordinated effort. The success of the Event Horizon Telescope project, which produced the first ever image of a black hole, stands as a powerful testament to this model. That iconic image was not the product of a single telescope, but of a virtual instrument the size of the Earth, created by synchronizing data from 8 independent observatories across the globe. Making that work required an unprecedented level of coordination among astronomers, electrical engineers, software developers, and even experts in atomic clocks to ensure perfect timing. They had to overcome not just technical barriers, but human ones' different management styles, funding cycles, and cultural approaches to problem solving across continents. Their triumph was as much a feat of diplomacy and project management as it was of astrophysics. This human element, the messy, complicated, and often frustrating work of building consensus and forging a shared identity, is the invisible scaffolding upon which every great discovery is built. It transforms a collection of brilliant individuals into a single, focused intellect capable of achieving what no one person, or even one discipline, could ever accomplish alone. Yet this grand ambition to touch the cosmos does not exist in a vacuum. It unfolds here on Earth within a fragile biosphere and a society facing pressing challenges. So a profound and necessary question arises. In a world grappling with climate change, poverty, and resource scarcity, can we justify spending billions of dollars and immense human capital to look at the sky? This is the ethical dimension of the endeavor, a challenge that goes beyond physics and engineering into the realm of philosophy and social responsibility. The teams building these telescopes are not blind to this. They operate with a growing awareness that their quest for cosmic knowledge must be balanced with a duty to planetary stewardship. Consider the logistical footprint of a ground-based observatory in a place like Antarctica. The Antarctic Treaty System designates the continent as a natural reserve devoted to peace and science. This means every action taken there is scrutinized to prevent contamination and preserve its pristine nature. Building and operating a facility like the South Pole Telescope is a colossal undertaking. All materials, from the smallest screw to the largest generator, must be shipped in over thousands of miles, a process that itself burns vast quantities of fossil fuels. Once there, the station must generate its own power and heat, manage its waste, and ensure that not a single drop of oil or speck of plastic contaminates the ice. The solution isn't to abandon the science, but to innovate relentlessly in sustainability. Newer stations and telescopes are increasingly powered by renewable energy. The Princess Elizabeth Antarctica Research Station, for instance, is powered almost entirely by wind and solar. Waste is meticulously managed, with everything from human sewage to packaging materials being containerized and shipped back out for proper disposal. The goal is to leave no permanent mark, to ensure that the only legacy of these bases is the data they stream back to the rest of the world, not a scar on the landscape. The ethical calculus becomes even more complex for space missions. A single rocket launch, necessary to place a telescope like the James Webb into its orbit, releases hundreds of tons of carbon dioxide and other particulates into the upper atmosphere. While the scientific return is incalculable, the environmental cost is very real and must be acknowledged. Furthermore, space itself is becoming cluttered. Defunct satellites, spent rocket stages, and other debris now populate Earth's orbit, creating a hazard for future missions. Responsible space agencies now mandate end-of-life plans for their spacecraft. The James Webb Space Telescope, for example, was placed at a gravitationally stable point 1 million miles away, where it will not interfere with other orbital paths and can drift harmlessly for millennia. For telescopes in closer orbits, plans often include a controlled deorbit to burn up in the atmosphere or a move to a graveyard orbit once their mission is complete. This practice of celestial cleanup is becoming a non-negotiable part of the design process, a promise that our exploration does not permanently pollute the avenues we use to see the universe. Then there is the question of resources. The budget for a single major space telescope could fund countless terrestrial initiatives, vaccination programs, clean water projects, or renewable energy infrastructure. This is not a comparison scientists take lightly. The defense rests on several pillars. First, the pursuit of fundamental knowledge is a core part of what makes us human. It inspires new generations, drives technological innovation with widespread applications, and provides a unifying goal that transcends national borders. The technologies developed for the extreme sensitivity of these telescopes often find unexpected uses in medicine, computing, and materials science. Secondly, these projects are not typically funded from a pot of money that would otherwise go to social programs. They are often financed through specific science budgets, and their existence helps maintain a robust aerospace and technology sector that employs thousands. The challenge, then, is not to halt the science, but to ensure that society is simultaneously addressing its urgent earthly problems. The scientific community increasingly recognizes that it must be a good global citizen, advocating not only for funding for space exploration, but also for the resources needed to solve problems here at home. This balanced perspective is crucial for maintaining public support and ensuring that the noble quest to understand our origins is conducted with a clear conscience and a respectful eye on its impact on our only home. These extraordinary demands are precisely what is driving a quiet revolution in material science, a field that has become the unsung hero in the quest to see the Big Bang. We are asking these telescopes to do the impossible, to remain perfectly stable while swinging between the scorching heat of the sun and the deep shadow of space, to be feather light for launch yet rock solid in operation, and to conduct electricity with perfect efficiency while being colder than anywhere in the natural universe. Conventional materials simply fail under these paradoxical conditions. This is why researchers are venturing into the lab to cook up entirely new substances, materials engineered not for the world we live in, but for the unforgiving extremes where these telescopes must thrive. Consider the simple yet monumental challenge of the telescope's structure itself. Every kilogram launched into space costs tens of thousands of dollars, so the entire assembly must be incredibly light. Yet, it must also be incredibly stiff and stable, a structure that flexes even a micron under the stress of deployment or the constant minute adjustments of its pointing system will throw off measurements with disastrous consequences. The answer has been a wholesale shift from traditional metals to advanced composites, carbon fiber reinforced polymers. The same materials used in Formula One cars and modern aircraft are now the default choice. Their magic lies in an unparalleled strength-to-weight ratio and something even more critical, a near-zero coefficient of thermal expansion. This means that as the temperature plummets from a balmy room temperature on the launch pad to the deep cryogenic chill of operation, these materials barely change size at all. They don't warp, twist, or contract in ways that would misalign the exquisitely tuned optics. This stability is what allows a mirror measuring meters across to maintain its perfect shape, ensuring that every precious photon is guided precisely to its target. But the real magic happens at the detector level, where the materials transition from the merely advanced to the truly exotic. Here, the quest is for substances that can enter the quantum realm of superconductivity. Materials like niobium titanium or niobium tin alloys are fashioned into tiny wires and circuits. When chilled to their critical temperature, which for these alloys is around 10 Kelvin, they lose all electrical resistance. This allows them to carry persistent currents without any loss of energy, a property that is harnessed to create incredibly powerful magnets for adiabatic demagnetization refrigerators, and more directly to form the basis of the transition edge sensors themselves. The detector element might be a microscopic strip of tungsten, a material chosen because its superconducting transition temperature can be meticulously tuned to sit right at the precise operating temperature of the cryostat, making it an exquisitely sensitive thermometer. Perhaps the most futuristic innovations are emerging in the realm of metamaterials. These are not defined by their intrinsic chemical properties, but by their precise physical structure, which is engineered at a microscopic scale to manipulate electromagnetic waves in ways nature never intended. For telescope optics, this could mean designing a lens that is not a heavy, solid piece of glass but a thin, lightweight film etched with a complex pattern of microscopic antennas. This metamaterial lens could focus microwaves with perfect efficiency without the immense weight and cooling challenges of a traditional mirror. Similarly, silicon nitride is being used to create membranes so thin and mechanically quiet that they barely vibrate at the molecular level, a crucial property for isolating detectors from even the faintest background noise. Alongside them, amorphous metals or metallic glasses are finding use. Unlike crystalline metals, which have a regular atomic structure that can create weak points, amorphous metals have a chaotic, glass-like atomic arrangement, making them incredibly strong, hard, and resistant to the microscopic cracking that can be caused by repeated thermal cycling. This combination of radical new substances is what transforms a theoretical design on a whiteboard into a physical instrument capable of surviving the journey and performing its delicate task, turning the dream of seeing the first light into a tangible reality. Even as we push materials and cooling systems to their absolute limits, we are beginning to bump up against a barrier that is not just engineering but fundamental: the laws of quantum mechanics themselves. At the temperatures and scales we are operating, the universe gets fuzzy. Heisenberg's uncertainty principle tells us there is a fundamental limit to how precisely we can know certain pairs of properties, like the position and momentum of a particle. For our detectors, this translates into a baseline of quantum noise, a faint, irreducible hiss that is woven into the very fabric of reality. It's the ultimate floor below which we cannot go with classical physics. To peer beyond this veil, to hear the whispers that are quieter than this quantum static, we must fight quantum with quantum. This is where the emerging field of quantum sensing and metrology steps in, not just as an upgrade, but as a complete paradigm shift in how we measure the universe. The first application of this is in amplification. In a standard telescope, after a detector picks up a faint signal, it needs to be amplified before it can be read out and analyzed. But the amplifiers themselves, even the best ones, add their own layer of electronic noise. A quantum-limited amplifier is a device engineered to push this added noise down to the absolute minimum allowed by the laws of quantum mechanics. It doesn't violate Heisenberg. It cleverly works within those rules to concentrate all the inherent uncertainty into one property of the signal, allowing the other property to be measured with near-perfect clarity. By using superconducting circuits that operate at the quantum level, these amplifiers add almost no additional disturbance, preserving the integrity of that precious, faint cosmic signal all the way through the data chain. This alone can effectively double the sensitivity of our detectors without making the telescope any larger, simply by letting us hear what we were already collecting with far greater fidelity. But the real magic, the true revolution, lies in even more exotic quantum phenomena, squeezed light and entanglement. Imagine the light you're trying to measure is like a wave on the ocean. Classical light has uncertainty in both its amplitude, the height of the wave, and its phase, the precise timing of its peak. The uncertainty principle says you can't know both perfectly at the same time. There's always a jitter. Squeezed light is a specially prepared quantum state where you deliberately sacrifice precision in one of those properties to gain extraordinary precision in the other. It's like choosing to make the wave's timing slightly fuzzy so that you can measure its height with absolute perfect certainty. For measuring the minuscule intensity changes in the cosmic microwave background, this is a game changer. By squeezing the light either before it hits the detector or even in the way the detector itself operates, we can effectively suppress the quantum noise that would otherwise drown out the signal we're after. Then there's entanglement, arguably the strangest and most powerful phenomenon in quantum mechanics. This is the spooky connection where two particles become linked, and measuring the state of one instantly tells you the state of the other, no matter the distance between them. For metrology, this isn't about spooky communication. It's about creating a form of quantum correlation that is sharper and more precise than anything possible with independent particles. An entangled network of sensors, in theory, could act as one giant, super-sensitive eye, allowing measurements that have a precision which scales not with the square root of the number of detectors, as in classical physics, but directly with the number of detectors. This is a monumental difference. It suggests a path forward where we don't just incrementally add more pixels to our cameras, but where we wire them together with quantum links to create an instrument whose whole is vastly greater than the sum of its parts. While many of these applications are still in the experimental stage, being tested on lab benches, their potential is staggering. Atomic sensors, which use the quantum states of individual atoms as exquisitely precise references, could provide a new way to calibrate our instruments against a fundamental standard of nature, reducing systematic errors to an unprecedented low. The entire endeavor is a move from simply trying to build bigger and colder to building smarter and more quantum aware. We are learning to sculpt the quantum vacuum itself, to manipulate the fundamental uncertainties of nature to our advantage. This isn't just another technical step, it's a leap into a new way of observing. It promises to redefine the very limits of astronomy, transforming our telescopes from powerful classical instruments into truly quantum, enhanced observatories capable of listening to the faintest echoes of time itself. But achieving these incredible temperatures is only half the battle. The real engineering marvel lies in maintaining that profound cold, not just for hours, but for years on end, in the most hostile environments imaginable. This relentless demand has pushed cryogenics, the science of extreme cold, from a niche field into a forefront of technological innovation. The journey began with relatively simple, if bulky, solutions. For decades, the workhorse of deep cooling was the liquid helium bath. Imagine a giant, super-insulated thermos bottle, or duor, filled with liquid helium boiling away at a frigid 4.2 Kelvin. This method works, but it's incredibly inefficient and logistically nightmarish. The helium constantly evaporates, requiring regular and expensive refills, a deal breaker for a remote telescope in Antarctica, let alone a spacecraft millions of miles from home. This limitation sparked a revolution, driving the development of closed-cycle mechanical refrigerators that could achieve and sustain ultra-low temperatures without constant replenishment. The stars of this new era are machines with names that sound like science fiction: pulse tube coolers and dilution refrigerators. A pulse tube cooler is a thing of elegant simplicity. It uses pressurized helium gas, not as a liquid but as a working fluid. By using oscillating pressure waves generated by a piston, it creates a temperature gradient along the length of a tube, effectively pumping heat from the cold end to the warm end. The beauty of this design is that the piston is physically separated from the cold head by the pressure wave itself, meaning there are no moving parts in the coldest section. This eliminates a major source of vibration and mechanical wear, making them incredibly reliable and perfect for the sensitive environment of a telescope. They are the workhorses that can efficiently bring entire systems down to temperatures around 4 Kelvin. But to plunge even further to that crucial realm below 1 Kelvin requires a different kind of magic, the dilution refrigerator. This device exploits the unique quantum properties of a mixture of the two isotopes of helium, helium-3 and helium-4. When this mixture is cooled below 0.87 Kelvin, it undergoes a spontaneous separation, like oil and water, into two distinct phases. By continuously circulating the helium-3 atoms through this phase boundary, engineers can create a continuous cooling effect, much like the evaporative cooling you feel when sweat dries on your skin, but on a quantum level. This process can reliably maintain temperatures as low as 0.01 Kelvin for years at a time, providing the perfectly still, cold environment that the most sensitive detectors demand. The integration of these systems, a pulse tube cooler pre-cooling the stages of a dilution refrigerator, creates a thermal ladder, a step-by-step descent into the deep cold that is both powerful and remarkably stable. For space missions, the challenges multiply and the solutions become even more ingenious. Here, every watt of power is precious and every gram of weight counts. This is where passive thermal management becomes as important as active cooling. The James Webb Space Telescope provides a masterclass in this approach. Its now iconic multi-layered sunshield is a passive thermal marvel. Each layer is as thin as a human hair, coated with reflective aluminum and treated silicon, designed to reflect the sun's intense heat and radiation back into space. This single structure creates a temperature difference of over 300 degrees Celsius between its sun-facing side and the instrument side, passively cooling the telescope's optics and instruments to about 40 Kelvin. This passive cooling dramatically reduces the load on the active mechanical coolers, which then only have the much smaller job of taking those already chilled components down to their final, operational deep cryogenic temperatures. This hybrid strategy of combining massive passive radiators with compact, ultra-efficient active coolers is the gold standard, enabling long-duration missions without consuming impossible amounts of power. These innovations in managing the flow of heat, of creating ordered cold from chaotic energy, are what transform a theoretical possibility into a practical observatory, allowing us to finally listen to the universe's oldest story without the constant crackle of thermal interference. After achieving the profound stillness required to collect the signal, we face the monumental task of making sense of it all. The raw data streaming from those ultra-sensitive detectors is not a clean, beautiful picture of the infant universe. It is a chaotic, roaring river of noise. It contains the faint cosmic whisper we desire, but it is buried under a crushing weight of instrumental hiss, the static of our own galaxy, and the fleeting shrieks of cosmic rays. Transforming this cacophony into a clear, reliable map of the Big Bang's afterglow is perhaps the most underappreciated triumph in this entire endeavor, a feat that relies entirely on a silent revolution in computational power and algorithmic cleverness. The sheer scale of the data is almost incomprehensible. A next-generation telescope doesn't just take a snapshot, it scans the sky continuously, with its tens of thousands of detectors, each taking readings millions of times per second. This relentless data collection generates a flood of information measured in petabytes. To put that in perspective, the entire processing power used by the Planck satellite mission, which produced our best all-sky map of the cosmic microwave background to date, involved thousands of central processing units running for months on end. That was a Herculean effort for its time, but the data volumes we're talking about for new projects like the Simons Observatory or CMB-S4 are orders of magnitude larger. Handling this deluge would be utterly impossible with the computing technology of just a decade ago. This is where the rise of exascale computing and specialized hardware becomes a true game changer. Scientists are now leveraging the same powerful graphics processing units, or GPU, that drive high-end video games and artificial intelligence research. Why GPU? Unlike a standard CPU, which is a powerful generalist, a GPU is a massively parallel processor containing thousands of smaller, efficient cores designed to handle multiple simple calculations simultaneously. This architecture is perfectly suited to the task of astronomy data processing, which often involves performing the same simple mathematical operation like applying a filter or performing a Fourier transform on billions upon billions of individual data points. By building supercomputing clusters packed with these GPUs, researchers can now process in days what once would have taken years, effectively enabling a form of real-time analysis that allows them to monitor the health and performance of their telescope almost instantly. But the hardware is only half the story. The real artistry lies in the algorithms, the sophisticated recipes of mathematical code that perform the actual purification. The first and most crucial step is a process called mapmaking. Remember, the telescope doesn't see the sky as a finished image. It scans back and forth, with each detector recording a long, convoluted time-ordered data stream that represents its journey across the cosmos. The map-making algorithm's job is to take this gigantic, tangled list of millions of measurements and reassemble it into a coherent, two-dimensional picture. This is an inverse problem of staggering complexity, requiring the algorithm to simultaneously solve for the true sky signal while also modeling and subtracting the ever-present noise. It's like trying to reconstruct a magnificent mosaic from a billion scattered pieces while someone is constantly shaking the table. Next comes component separation. The telescope doesn't just see the cosmic microwave background. Its view is contaminated by foreground emissions from our own Milky Way galaxy, the glow of interstellar dust, and the synchrotron radiation from electrons spiraling in magnetic fields. These foregrounds are billions of times brighter than the subtle primordial signal. Teasing them apart requires another layer of algorithmic genius. Scientists use the fact that these different signals have unique spectral signatures. They glow with different intensities across various microwave frequencies. Advanced statistical techniques, particularly Bayesian inference, are employed to probabilistically separate these layers, much like a sophisticated audio engineering program can isolate a single singer's voice from a full orchestra recording. This method doesn't provide a single answer but a vast ensemble of possible sky maps, allowing researchers to quantify their uncertainty and have confidence in the final, cleaned result. And now, machine learning is injecting a powerful new tool into this process. While traditional algorithms are based on our explicit human understanding of the physics involved, neural networks can learn to recognize patterns implicitly. Researchers can train a neural network on millions of simulated skies, showing it examples that include both the perfect cosmic microwave background and all the known types of noise and foreground contamination. The network learns the subtle correlations and patterns that distinguish the true cosmic signal from the junk. When presented with real, messy data, it can then act like a supremely talented assistant, identifying and filtering out interference in ways that might be incredibly difficult for a human to program explicitly. This doesn't replace the physics-based algorithms, but it complements them, offering a new and powerful way to cross-check results and extract every last ounce of information from the precious data. This entire computational symphony, from the raw power of parallel processors to the elegant logic of Bayesian statistics and the pattern recognition prowess of AI, doesn't just manage data. It performs a kind of digital alchemy, turning the leaden roar of raw noise into the gold of cosmic revelation. This shift towards modularity represents a fundamental rethinking of how we build these cosmic time machines. Gone are the days of designing a single, colossal, and irreplaceable instrument, a monolithic masterpiece that is essentially frozen in technological time from the moment of its launch or construction. Instead, the new philosophy is to think in terms of ecosystems and networks. Imagine not one giant eye on the sky, but a coordinated swarm of smaller, identical eyes, all working together in perfect harmony. This is the core of the modular approach, and it's revolutionizing projects like the CMB-S4 experiment. Rather than constructing one impossibly large and expensive telescope with a mirror dozens of meters across, CMB-S4 will deploy an array of multiple smaller telescopes, each a self-contained unit with its own optics, detectors, and cryogenics. Some will specialize in mapping large swaths of the sky at lower resolution, while others will focus on smaller patches with ultra-high resolution. Together, they act as a single, powerful instrument, but with critical advantages that a monolithic design could never offer. The benefits of this strategy are profound, starting with a massive reduction in risk and cost. Building a single, unique, giant telescope is a high-stakes gamble. If a critical component in its complex, interconnected system fails after deployment, it can cripple or even doom the entire multi-billion-dollar investment. But with a modular array, if one telescope in the network experiences a malfunction, the others can continue observing. The system is inherently fault-tolerant. This philosophy also simplifies manufacturing. Instead of crafting one-of-a-kind components that require custom tooling and immense precision, engineers can design a single, optimized telescope module and then replicate it dozens of times. This mass production of identical units dramatically drives down costs through economies of scale and makes the manufacturing process far more reliable and predictable. Perhaps the most exciting advantage is future-proofing. Technology, especially in detector and computing fields, advances at a breakneck pace. A telescope designed and built over a decade could be equipped with technology that is nearly obsolete by the time it sees first light. A modular system shatters this constraint. Imagine that 5 years into an observatory's lifespan, a revolutionary new superconducting detector is invented. In the old model, there would be no way to incorporate it, but in a modular array, you could simply build new receiver modules featuring these advanced detectors and integrate them directly into the existing infrastructure. The older modules could be gradually phased out or repurposed, allowing the entire facility to evolve and improve continuously. This transforms the telescope from a static monument into a living, breathing entity that grows and adapts alongside the scientific questions it's trying to answer, ensuring its relevance and discovery potential for decades to come. This scalable, resilient model doesn't just build a tool for today's science, it builds a platform for tomorrow's discoveries. But even with the most sophisticated simulations and the most rigorous pre-launch testing, a telescope's performance can drift over time in the harsh reality of space. Detectors age, their sensitivity can change minutely, and optics can accumulate microscopic contaminants. This is why calibration, the process of checking the telescope's measurements against a known, trusted standard, is the final, non-negotiable guardian of data integrity. For generations, this has meant periodically pointing the entire observatory away from its science target and towards a celestial reference like Jupiter or a special region of the sky. But this method has its drawbacks. It takes precious time away from observing the cosmic microwave background, and it relies on sources that are themselves imperfect and can vary. The next great leap in precision comes from a brilliantly simple idea. Instead of looking outward for a reference, why not bring the reference with you? This is the promise of enhanced calibration using artificial sources, a breakthrough that transforms the telescope from a passive observer into a self-aware instrument, one that can constantly check its own health and accuracy. The goal is to create a known, stable signal that perfectly mimics the properties of the cosmic microwave background itself. Engineers are developing incredibly sophisticated artificial sources that can be built right into the heart of the telescope. One of the most powerful types is the cryogenic blackbody. In physics, a blackbody is a perfect absorber and emitter of radiation. By carefully machining a piece of material, like epoxy, mixed with conductive carbon black, and cooling it to a precisely known temperature within the cryogenic chamber, engineers can create a device that emits a near-perfect spectrum of microwave radiation. This artificial sky patch provides a benchmark. By periodically rotating a small mirror to let the detectors see this onboard blackbody, the instrument can answer a critical question. If we know exactly what signal we're sending, what do the detectors actually report? Any difference is a direct measurement of the system's drift or error, a calibration factor that can be immediately applied to all the subsequent science data. For the hunt for primordial gravitational waves, which imprint a specific pattern of polarization on the light, an even more advanced calibrator is needed. This requires a polarized emitter, a device that can produce a microwave signal with a specific, known polarization angle. Creating such a source that is also stable, compact, and able to operate at cryogenic temperatures is a monumental technical challenge. Some designs use a finely machined waveguide that twists the electromagnetic waves as they pass through. Others might use a rotating grating or a specially designed metamaterial surface. The key is that it provides a known polarization state, allowing scientists to check for and correct any subtle miscalibration in the detector's ability to measure the all-important twisting of the light waves from the early universe. The impact of this innovation is profound, turning calibration from a disruptive, periodic chore into a seamless, continuous process. Missions like the upcoming Light-Bird spacecraft are designing these artificial calibrators to operate constantly in the background. Imagine a tiny, super-stable beacon of light humming away inside the frozen darkness of the telescope's core. It's not unlike a musician constantly tuning their instrument between songs, ensuring every note is perfect without stopping the concert. This continuous internal reference allows for real-time monitoring of the detector's health. If a detector's response begins to drift by a fraction of a percent over the months and years, the calibration system will detect it instantly, allowing software to correct for it on the fly. This eliminates a whole class of potential systematic errors that could otherwise creep into the data undetected and masquerade as a revolutionary discovery. This shift represents a new level of maturity in our astronomical instruments. It moves us from hoping our telescope remains stable to actively knowing that it is. It builds a foundation of trust directly into the hardware, ensuring that the breathtaking map of the primordial universe we finally produce is not a beautiful but potentially flawed impression, but a true and reliable portrait. By making the telescope its own master reference, we close the loop on uncertainty, granting us the confidence to interpret the faintest whispers from the Big Bang, not as potential instrument glitches, but as the authentic voice of the cosmos itself. Yet hidden within that faint, ancient glow is an even subtler secret, a delicate pattern imprinted on the light itself that could be the ultimate prize. This is polarization, a specific orientation in the way those electromagnetic waves are vibrating as they travel across the universe. Most of the cosmic microwave background is unpolarized, its waves jiggling in every which direction. But a small fraction of this primordial light carries a unique signature, a preferred direction of vibration that was frozen into place by the physics of the early universe. This isn't just a minor detail, it's a fossilized imprint of the universe's most violent and transformative moment. The theory of cosmic inflation proposes that the universe underwent an unimaginably rapid exponential expansion in the first fraction of a second after the Big Bang. This violent stretching of spacetime itself would have generated ripples, powerful gravitational waves that literally shook the fabric of the cosmos. And just as a boat rocking on a pond creates a specific pattern of ripples in the water, those primordial gravitational waves would have left a unique, twisting pattern in the polarization of the cosmic microwave background. Finding this specific swirl, known as B-mode polarization, is the smoking gun for inflation. It would be our most direct evidence yet for what happened at the very dawn of time, a glimpse into energies and physics so extreme they can never be replicated in any laboratory on Earth. But seeing this pattern is perhaps the hardest measurement ever attempted in all of astronomy. The signal is incredibly faint, a whisper within a whisper. We are searching for a polarization signal that is over 1 million times weaker than the already faint temperature variations in the background radiation. To make matters even more challenging, our own Milky Way galaxy is a brilliant source of polarized light, created by interstellar dust and magnetic fields, which creates a foreground haze that must be meticulously peeled away. This requires not just incredible sensitivity, but an instrument that can measure across many different microwave frequencies simultaneously, acting like a pair of sophisticated sunglasses that can filter out the galactic glare to reveal the pristine cosmic signal beneath. The hunt for this signal is what is driving a revolution in detector technology, pushing us to invent entirely new ways to see. At the forefront are new generations of polarimeters, the specialized instruments designed to measure the orientation of light waves. Researchers are moving beyond traditional designs and turning to the world of metamaterials. These are not your ordinary materials. They are engineered structures with properties that don't exist in nature. A metamaterial-based polarimeter might use a microscopic, repeating pattern of antennas etched onto a silicon chip. This intricate design allows it to act as a super-efficient filter and sensor, capturing the polarization of incoming light with far greater efficiency and less noise than a conventional device. This is coupled with advances in how we read out the signals from these detectors. A technique called frequency domain multiplexing allows a single superconducting wire to carry the signals from dozens, or even hundreds, of individual detectors simultaneously. Each detector's signal is assigned a unique frequency, like different radio stations on a single broadcast band. This drastically reduces the number of wires needed, which in turn reduces the heat load and complexity inside the ultra-cold cryostat, making it possible to build cameras with an unprecedented number of pixels. We are now entering the era of the mega camera. Projects like the Simons Observatory in Chile are building receivers that contain tens of thousands of these polarization-sensitive detectors, all working in unison. Imagine a single camera with over 50,000 individual eyes, each one capable of discerning the precise twist of a microwave photon that has been traveling for over 13 billion years. Each of those detectors is a masterpiece of nanofabrication, and each one must be perfectly characterized and aligned. A misalignment of even a few degrees across the entire array could create a false polarization signal that would perfectly mimic the cosmic swirl we are desperately searching for, leading us down a path of false discovery. This demands a level of precision that borders on the obsessive. Engineers use precise robotic systems to assemble these arrays, and they develop complex calibration routines that use both artificial sources and observations of known celestial objects to map and correct for the tiniest imperfections in every single detector. This isn't just building an instrument, it's tuning a colossal cosmic violin, ensuring every string is in perfect harmony to play the music of the universe's birth. This transformational focus on polarization is more than a technical upgrade. It represents a fundamental shift in how we explore the cosmos. For decades, we have studied the universe by analyzing the intensity of its light, how bright it is across different colors. Polarization adds a rich new dimension to our vision, a way to read the hidden geometry and dynamics of the universe's earliest moments. It's the difference between listening to a symphony and being able to see the conductor's baton, revealing the forces that directed the entire performance. By mastering this subtle language of twisted light, we are building a new window, one that looks not just back to the first light, but back to the first vibrations, the first tremors of spacetime itself, offering us a chance to witness the very trigger that set our entire cosmic story into motion. Now imagine a telescope that can not only endure the harsh silence of its environment, but can also think for itself. This is the new frontier of autonomous operation, where these cosmic observatories are evolving from complex machines into intelligent partners in discovery. The sheer complexity of managing a telescope like the Atacama Cosmology Telescope, which must execute intricate scanning patterns while constantly monitoring its own health, is more than any human team could handle in real time from thousands of miles away. The solution has been to embed a form of artificial intelligence directly into its control systems, creating an autonomous entity capable of making its own decisions. This isn't about replacing human scientists. It's about empowering them by offloading the tedious, constant oversight to a system that never sleeps, never gets tired, and can react to changing conditions in milliseconds. This autonomy manifests in several critical ways, starting with the most fundamental task, what to look at and when. The observing schedule for these instruments is a complex puzzle. Certain scientific goals require staring at a specific patch of sky for weeks to build up signal, while other targets are time-sensitive, like catching a fleeting atmospheric phenomenon or coordinating with other telescopes for a multi-wavelength campaign. Add to this the unpredictable nature of the environment, a sudden gust of wind that shakes the telescope, a change in atmospheric water vapor that degrades the quality of the observation, or a spike in detector noise, and the schedule becomes a dynamic, living thing. Autonomous systems use sophisticated algorithms to constantly weigh these competing priorities. They can analyze real-time weather data from on-site sensors, assess the current performance of the instrument, and then dynamically reschedule the night's observations on the fly. If clouds roll in or the humidity rises too high for sensitive microwave measurements, the system doesn't just wait for a human to respond to an email alert. It immediately pivots to a backup plan, perhaps switching to a different frequency band that's less affected or moving to a different part of the sky that is still clear. This ensures that not a single precious minute of observing time is wasted. Beyond scheduling, this intelligence extends to the telescope's very health. The onboard software is packed with fault protection routines and watchdog algorithms that perform a constant, silent diagnosis of the entire system. It monitors thousands of data streams, voltages, temperatures, pressures, motor currents, looking for the slightest anomaly that might indicate a component is beginning to fail. If it detects a problem, it doesn't panic. It executes a pre-programmed series of responses. A slight overheating in a readout module might trigger it to power cycle that specific unit. A misalignment in the pointing could cause it to initiate a safe stow sequence, protecting the hardware until the issue can be diagnosed. For more serious faults, it can place the entire telescope into a safe mode, a stable holding pattern where it points away from the sun and awaits instructions from Earth. This capability is absolutely vital for resilience, allowing the telescope to protect itself from cascading failures during the long, unstaffed Antarctic winter or while orbiting alone 1,000,000 miles from home. The driving force behind this shift is a combination of smarter software and more capable hardware. Machine learning models trained on vast historical datasets of telescope operations can now predict problems before they even occur. By recognizing subtle patterns in the data that precede a known failure mode, the system can schedule preventative maintenance or alert human operators weeks in advance. This predictive maintenance is a game changer, transforming operations from a reactive process of fixing broken things to a proactive science of preventing breaks altogether. This level of self-awareness turns the telescope from a passive tool into an active collaborator, an intelligent observatory that is not only collecting data, but also tirelessly optimizing its own performance to ensure that the data it sends back is of the highest possible quality. It represents the final layer in our quest to build the perfect instrument, one that can not only see the faintest echoes of the Big Bang, but can also ensure it is always listening at its absolute best. This spirit of openness, of sharing not just the polished results but the raw data and the tools themselves, has become one of the most powerful catalysts in modern cosmology. The sheer scale of cosmic microwave background research means that no single team, no matter how brilliant, can possibly wring every last secret from the petabytes of data their telescopes collect. It's an impossible task, so instead of hoarding this treasure, the community has embraced a radically different philosophy. They throw the doors wide open. Almost as soon as the data is calibrated and verified, it's uploaded to vast public archives where any researcher from any institution in any country can download it and begin their own investigation. This isn't a minor courtesy, it's a fundamental shift in how science is done, transforming a competitive race into a collaborative global endeavor. Central to this movement are platforms that act as the digital libraries of the cosmos. The NASA Astrophysics Data System is the grand central station for published papers, a free portal that gives anyone with an internet connection access to centuries of astronomical research. But the openness goes far deeper than just the final papers. Repositories like Zenodo and RZiv allow scientists to share everything: the raw data streams, the complex computer code used to process it, the preliminary results, and even the negative results that didn't lead to a breakthrough. This creates a level of transparency and reproducibility that was unheard of a generation ago. A graduate student in India can now download the exact same dataset that a professor at an Ivy League school is using, apply their own unique algorithms, and potentially see something everyone else missed. This democratization of data breaks down traditional barriers of privilege and access, allowing talent and curiosity to flourish anywhere on the planet. The collaborative ethos extends powerfully into the realm of software. The data processing pipelines for these telescopes are not secret, proprietary codes locked away in a lab. They are almost universally open source, published on platforms like GitHub for the entire world to see, use, and improve. This means that a young postdoctoral researcher can take the official data reduction software from the Planck satellite team, modify it to test a new statistical technique, and then share those improvements back to the community. This creates a virtuous cycle of innovation where the tools themselves get smarter and more robust through the collective effort of hundreds of contributors. It also acts as a built-in system of peer review. When your code is open for anyone to inspect, mistakes are found and corrected with breathtaking speed, ensuring the final scientific results are built on a rock-solid foundation. This strategic openness is far more than just academic generosity. It's a force multiplier of incredible power. By inviting thousands of the world's brightest minds to analyze the same data, we effectively create thousands of unique research teams, each with their own perspective, expertise, and questions. A theorist might look at a map of the cosmic microwave background and see evidence for a new type of particle. A data scientist might apply a novel machine learning algorithm and uncover a subtle systematic error that everyone else had overlooked. An astronomer who specializes in galaxy formation might cross-correlate the data with a new galactic survey and discover a previously unknown connection between the ancient universe and the large-scale structure we see today. This diversity of thought accelerates discovery at an exponential rate. A finding that might have taken a single team years to uncover can emerge in months through the combined effort of a global community, all because the data was set free for everyone to explore. This is how we build a true, inclusive scientific community, where the next great discovery can come from anywhere, and where our collective understanding of the cosmos expands at the speed of our shared curiosity. Yet this grand scientific endeavor reaches its truest potential not when it's locked away in research papers, but when it is shared with the world. The quest to see the Big Bang is fundamentally a human story, a shared adventure that taps into our deepest curiosity about where we come from. Recognizing this, the teams behind these monumental projects have made public engagement and educational outreach a core mission, not an afterthought. They understand that the billions of dollars and decades of effort required are ultimately a public investment, and they are committed to delivering a return that goes far beyond data. It delivers wonder, inspiration, and a renewed sense of our place in the cosmos. This isn't about dumbing down the science, it's about building bridges, using innovative tools and heartfelt storytelling to invite everyone to the frontier of discovery. The methods for this outreach are as sophisticated and creative as the telescopes themselves. Gone are the days of a dry press release accompanied by a single, grainy image. Now we have live-streamed deployment events that feel like high-stakes season finales, with millions of people around the world holding their breath as a sunshield unfurls a million miles away. We have stunning, high-resolution data visualizations that transform abstract numbers into swirling, colorful maps of the infant universe, tools that allow anyone to zoom in and explore the details for themselves. The release of the James Webb Space Telescope's first images was a masterclass in this new approach. It wasn't just a photo drop, it was a global media event. Each breathtaking image was paired with accessible explanations, comparison shots showing how much more detail Webb revealed than its predecessors, and even guides pointing out the specific scientific mysteries captured within the frame. This careful curation transformed the images from mere pictures into stories, allowing a teacher in a classroom, a student at home, or an artist in a studio to not only see the beauty but to grasp the profound significance of what they were witnessing. This work extends far beyond one-off events. Major projects now routinely host websites filled with interactive content, behind-the-scenes blogs from engineers and scientists, and dedicated educational portals with lesson plans tailored for different grade levels. They partner with planetariums and museums to create immersive exhibits where you can stand beneath a full-scale model of a telescope mirror or listen to the sound of data converted into an audible format. Some initiatives even embrace citizen science, creating platforms where volunteers can help classify patterns in data or search for anomalies, contributing directly to the research process. This inclusive approach shatters the old model of the isolated scientist in an ivory tower, rebuilding it as a global conversation where everyone has a seat at the table. It acknowledges that the drive to understand the universe is a universal human trait, and that by sharing the journey openly, we enrich the science itself with a diversity of perspectives and a wellspring of public goodwill. This engagement is what turns taxpayers into stakeholders and children into future innovators, ensuring that the quest to see the origins of everything continues to capture our collective imagination for generations to come. But how do you ensure that these digital blueprints accurately reflect the chaotic realities of the real world? The answer lies in the sheer, staggering depth of these simulations. They don't just model the telescope, they attempt to create a perfect digital twin of its entire existence. This starts with the most fundamental component, the simulated sky itself. Scientists generate a perfect, idealized map of the cosmic microwave background, complete with the specific patterns of temperature and polarization they hope to find. Then they layer on a realistic simulation of all the foreground noise, the swirling, polarized glow of the Milky Way's dust, the synchrotron radiation from its magnetic fields, and the faint whispers of distant galaxies. This creates a synthetic but hyper-realistic sky, a known truth against which the virtual telescope can be tested. Into this digital universe, the simulated telescope is born. Its every component is modeled with painstaking accuracy. The simulation doesn't just know the shape of the primary mirror, it knows its precise material properties, how it will expand and contract with temperature changes, how its surface might have microscopic imperfections from the polishing process. It models the performance of each individual detector, assigning it unique characteristics based on real-world test data. This one is 10% noisier, that one has a slightly non-linear response to bright signals. The software simulates the subtle vibrations from the cryogenic coolers, the minute flexing of the structure as it scans across the sky, and even the way stray light might bounce around inside the telescope tube and accidentally land on a detector, creating a ghost signal. For ground-based telescopes, the simulation includes a dynamic, rolling model of the atmosphere above the site, with virtual water vapor cells drifting and evolving, subtly distorting the incoming microwaves in real time. This isn't a simple animation. It's a running physics engine that calculates the interaction of every single photon with every single component, from the moment it hits the primary mirror to the instant it is converted into a digital data point. This virtual sandbox becomes an invaluable playground for optimization. For a project like CMBS-4, which will use an array of multiple telescopes, teams can run thousands of different simulations. They can test different array configurations. Should the telescopes be clustered closely together for a compact, high-resolution core, or spread far apart to better capture the large-scale patterns on the sky? They can experiment with countless scanning strategies, slow, smooth sweeps versus faster, jerky motions, calculating how each approach affects both the coverage of the sky and the introduction of potential systematic errors from the movement itself. They can literally break things on purpose in the simulation, short out a detector, misalign a mirror by a fraction of a degree, have a cooler fail, and observe exactly how that failure propagates through the data. This allows them to identify single points of failure and redesign for redundancy long before any metal is cut. This shift from physical trial and error to digital predictive engineering is perhaps one of the most significant cost-saving breakthroughs. It turns what was once a process of building, testing, breaking, and rebuilding an incredibly expensive cycle into one of rapid, cheap, virtual iteration. The final design that emerges from this gauntlet of digital stress testing is not a first draft. It's a mature, proven entity, already perfected in the world of silicon and code, giving everyone the confidence that when the real steel and superconductors are finally assembled, they will work as intended from the very first moment they look up. Yet for all their incredible sensitivity to the primordial universe, cosmic microwave background telescopes have a kind of blindness. They are specialists, tuned to hear one specific, ancient note in the cosmic symphony. But the universe composes its history across the entire electromagnetic spectrum, with each wavelength, from radio waves to gamma rays, telling a different part of the story. To get the full, rich narrative, we can't just rely on one instrument. We need to combine the perspectives of many. This is the power of multi-wavelength astronomy, a collaborative approach that is transforming our understanding by weaving together disparate threads of light into a single, coherent tapestry. It's the difference between listening to a single instrument practice and hearing the entire orchestra perform together. The music only makes complete sense when all the parts are heard in unison. Take the cosmic microwave background itself. A telescope like Planck gives us a stunning baby picture of the universe, but it's a picture that has been obscured and contaminated over billions of years. The journey of that ancient light to our telescopes is fraught with interference. It passes through vast clouds of interstellar dust that glow in the infrared, through galaxies bursting with stars that shine in optical light, and through the magnetized plasma between galaxies that emits radio waves. All of these foreground sources create a haze that must be meticulously cleaned away to reveal the pristine primordial signal beneath. How do we do that? We call upon other telescopes, specialists in these other wavelengths, to act as guides. An infrared space telescope like the Herschel Observatory can map the specific structure and intensity of that interstellar dust. By comparing the Herschel dust map with the haze seen by Planck, astronomers can digitally subtract the contamination, leaving behind a much clearer view of the true cosmic microwave background. It's a cosmic cleaning process where one telescope's noise is another telescope's signal. This cross-correlation extends far beyond simple cleaning. It allows us to test our theories in a much more profound way. One of the most powerful techniques involves comparing the Planck map of the early universe with giant optical surveys that map the late universe, like the Sloan Digital Sky Survey. These optical telescopes painstakingly chart the positions of millions of galaxies, revealing the immense cosmic web of dark matter that structures our modern universe. The theory of cosmic inflation makes a specific prediction. The tiny density fluctuations frozen into the cosmic microwave background should be the direct seeds for the giant galaxy clusters we see today. By using sophisticated statistical methods to cross-reference the Planck map with the Sloan galaxy map, scientists can literally connect the dots. They can trace a line from a slightly warmer spot in the infant universe, a gravitational seed of more matter, directly to the location of a massive supercluster of galaxies billions of years later. This isn't just consistent with our models, it's a direct validation of the entire story of cosmic evolution, from the first fraction of a second to the present day. It turns a theoretical timeline into an observed empirical fact. This integrative philosophy is now fundamentally shaping how new telescopes are designed and built. They are no longer conceived as isolated marvels, but as key players in a global network of observatories. The upcoming Nancy Grace Roman Space Telescope, an infrared observatory, and the Vera C. Rubin Observatory, an optical survey machine, have their own primary science goals, but their observing schedules are being carefully coordinated with cosmic microwave background projects like the Simons Observatory. The goal is to ensure that as these telescopes scan the sky, they are often looking at the same patches of the universe at around the same time, creating incredibly rich multi-layered datasets. This allows for a form of scientific triangulation that is far more powerful than any single observation. A mysterious feature seen in the microwave background can be instantly checked against infrared and optical data to see if it has a counterpart, helping to distinguish a true cosmological signal from a mere instrumental artifact. This holistic strategy is a testament to a growing maturity in astronomy, a recognition that the universe is a complex, interconnected system, and that to truly understand it, we must observe it in all its many forms of light, creating a picture that is not just deeper but truer. Yet, even as we push the boundaries of quantum sensing and data processing, our view of the cosmos faces a growing threat from our own civilization's glow. The very technological progress that enables these incredible telescopes also creates an invisible shroud of interference, a blanket of light and radio noise that slowly obscures the faint signals from the depths of space. This isn't merely an inconvenience, it's an existential challenge for astronomy, forcing a new kind of innovation that isn't about building better instruments, but about defending the clarity of the sky itself. The most remote deserts and highest mountaintops, once considered pristine sanctuaries for observation, are now under siege. The relentless expansion of cities sends a dome of light pollution sprawling across the night sky, while our insatiable demand for wireless communication fills the radio spectrum with a cacophony of signals that are billions of times louder than the cosmic whispers we seek to hear. The fight against this encroaching noise is being waged on multiple fronts. Technologically, astronomers are developing increasingly sophisticated filters and signal processing algorithms designed to identify and subtract human-made interference from their data. Imagine a software that can recognize the distinct digital fingerprint of a cell phone tower or a satellite transmission and digitally erase it from the observations, much like noise-canceling headphones silence the rumble of an airplane engine. These are not perfect solutions, however. They can only clean the data so much, and they often require knowing the exact nature of the interfering signal, a constant game of catch-up as new technologies emerge. For the most sensitive observations, particularly the hunt for the primordial polarization of the cosmic microwave background, there is no substitute for absolute radio silence. This has led to a parallel, crucial effort in legislation and preservation. Astronomy projects are now proactively working with governments to establish radio-quiet zones around their observatories, areas where certain transmission frequencies are restricted or prohibited by law. The Square Kilometre Array project stands as a monumental example of this forward-thinking approach. This next-generation radio telescope, designed to be the most sensitive ever built, is being constructed across vast, sparsely populated regions of South Africa and Western Australia. But its leaders knew that simply finding a remote location wasn't enough. They successfully lobbied for national legislation in both countries to protect the radio spectrum around the telescope sites. These laws strictly limit future development of wireless networks, radar systems, and other emitters in the area, creating a protective bubble that will shield the instrument for decades to come. This is a profound commitment, a recognition that the value of this cosmic window is so great that it warrants curbing certain types of technological expansion in its vicinity. It transforms the telescope from a mere scientific instrument into a designated natural reserve for the ether, a protected habitat for silence. This endeavor transcends mere technical necessity and enters the realm of global stewardship. It forces a difficult but essential conversation about balancing humanity's drive for connectivity and growth with the preservation of our ability to explore the universe. The fight for dark skies is not just for astronomers, it is for everyone. The loss of a truly dark night sky to light pollution severs a connection to the cosmos that has inspired art, science, and philosophy for all of human history. In protecting these windows to the universe, we are not just safeguarding data points for scientists. We are preserving a fundamental human experience, the ability to look up and wonder at the majesty of the stars. This makes astronomy a critical test case for a new kind of sustainable development, one that measures progress not only in economic terms, but also in its ability to coexist with our innate need for discovery and our connection to the cosmos beyond our planet. But what do you do when the data is so vast and the patterns so subtle that even the world's most powerful supercomputers need a little help? You call in the crowd. This is the beautiful and increasingly vital world of citizen science and distributed computing, a paradigm shift that recognizes that the quest to understand the cosmos isn't just for those with PhDs and access to a supercomputer cluster. It's for anyone, anywhere, with a curious mind and a willingness to lend their eyes, their intuition, or even just the spare processing power of their home computer to the cause. This isn't about outsourcing busy work, it's about tapping into a global network of human and computational intelligence, transforming the public from passive observers into active participants in the grandest detective story of all. Consider the sheer scale of the data. Even after the most sophisticated algorithms have done their initial cleaning, there often remain tasks that are incredibly difficult to automate but remarkably well suited to the human brain's innate pattern recognition abilities. We're talking about the painstaking work of classifying strange glitches in the data, identifying the faint, wispy trails of distant galaxies that might be contaminating the signal, or spotting anomalous patterns that could be a sign of a systematic error or just maybe a revolutionary discovery. This is where platforms like Zooniverse have become indispensable. Researchers can upload thousands, even millions, of snippets of data to these platforms, and volunteers from around the world can log on and begin sorting through them. It's like a cosmic version of Where's Waldo, where each participant's small contribution is aggregated into a powerful statistical consensus. The collective judgment of tens of thousands of volunteers, each bringing their own unique perspective, often proves to be more accurate and robust than any single algorithm could ever be, catching subtleties that a computer might dismiss as mere noise. Alongside this army of human classifiers is an even larger silent workforce, a global grid of distributed computing. Projects like Cosmology at Home and Einstein at Home operate on a brilliantly simple principle. The data processing required for cosmology involves running millions of slightly different simulations, testing how well various theoretical models fit the observations. This is a perfectly parallelizable task. Each simulation can run independently on a separate computer. Instead of building one impossibly expensive supercomputer, these projects ask volunteers to install a small, safe program on their personal computers. Whenever your machine is idle, when you're sleeping or at work, or just reading an article, the program quietly downloads a small chunk of data, processes it, and sends the result back to the researchers. It's a modern-day barn-raising, but for computational power. Millions of ordinary laptops and desktops around the world collectively form a massively powerful, distributed supercomputer, one that operates at a scale and cost that would be unimaginable through traditional means. The impact of this model is twofold, and both aspects are profound. First, it dramatically accelerates the pace of research. An analysis that might have taken a dedicated university computing cluster years to complete can be finished in months or even weeks through the combined power of this global network. This speed allows scientists to test more theories, run more simulations, and iterate on their ideas with an agility that was previously impossible. But the second, and perhaps more important, impact is the democratization of science itself. These projects shatter the ivory tower, inviting everyone to have a direct hand in cutting-edge discovery. A school teacher in Brazil, a retiree in Japan, and a student in Norway can all point to a discovery and say, "I helped find that." This fosters a deep, personal connection to the scientific process, building public trust and engagement in a way that press releases and polished documentaries never could. It serves as a powerful reminder that building a telescope to see the Big Bang is not just a technical endeavor. It is a deeply human one, a collective project that draws on the curiosity and goodwill of people across the globe, weaving them directly into the fabric of our understanding of the universe. Building a telescope that can see back to the Big Bang is one of humanity's most profound technical and scientific undertakings, a monumental endeavor that stretches our understanding of physics, engineering, and our own collective capabilities. This isn't just about creating a bigger lens or a more powerful sensor. It's about redefining the very limits of observation. To capture the universe's first light, we've had to pioneer advances in virtually every field imaginable. We've engineered detectors so sensitive they can register the heat of a single photon from across the cosmos. And we've built cryogenic systems that can create pockets of cold more profound than anywhere in the natural universe, all to silence the thermal noise that would otherwise drown out the faint whispers of creation. We've developed computational algorithms powerful enough to process oceans of data, sifting the signal from an overwhelming avalanche of interference. And perhaps most importantly, we've learned to collaborate on a global scale, uniting nations and disciplines behind a single, shared goal that transcends borders and politics. This journey has taken us from the frozen, silent deserts of Antarctica to the pristine vacuum of space, with teams of brilliant minds pushing technology to its absolute breaking point in the most extreme environments we can access. Each new breakthrough, whether in revolutionary materials science, the strange world of quantum sensing, or the raw power of exascale computing, represents another step forward in this grand quest. These aren't just incremental improvements, they are leaps of imagination that bring us closer than ever to answering the most fundamental questions we can ask. Where did everything come from? How did the universe begin? And what is our place within this vast cosmic story? The pursuit of these answers is what drives us to overcome seemingly impossible challenges, to spend decades and billions of dollars on a machine designed to look backward in time. But as we stand on the brink of these potential discoveries, it's vital to remember that this endeavor is about so much more than the machinery itself. The telescopes, the detectors, the supercomputers, these are merely the tools. The true heart of this quest is something deeply and uniquely human. Our innate, insatiable desire to understand our origins, to find our context in the cosmos, and to connect with the very beginning of everything. It is a project that speaks to our deepest curiosity and our most ambitious spirit, a testament to what we can achieve when we dare to look up and wonder.